This graph is very satisfying.
I know, it's so good. Welcome to part 3 of a tutorial of Reverse Engineering Modular Addition. In the previous part, we dug through the final model checkpoint, looked at a bunch of model internals, and broadly figured out what on earth was actually going on inside. This was slightly janky and constrained by the fact that I was trying to code things on the fly, so you should totally go check out the paper and our code there for a more detailed and rigorous approach. But this hopefully gave you the gist. My underlying philosophy of our grokking paper is we're confused about what the hell is going on with grokking. The way you become less confused is you try to really deeply understand something. In this case, the final fully trained model and how it did modular addition. And then you try to distill this understanding into some metrics or visualizations or tests that you can run on a much broader range of models and try to figure out the underlying principles here and how you can use them to actually understand what's going on. I think it's important to begin with the what the hell is going on in a single model because it's really, really easy to trick yourself and form false beliefs about something or otherwise just be kind of confused and do things that don't really track the ground truth. But now we've actually understood what is going on in the modular addition system, we can now try to distill them out into things that will let us look at what's going on during training and try to figure out what is up with the grokking, what's going on internally, and trying to poke around at the model internals. The tool we're going to use here is this idea of progress measures. The idea of a progress measure is sometimes models do weird stuff suddenly. The jargon for this is emergence, where models are bad at something and then suddenly become good at it. And the idea of a progress measure is what if we can find some metric for the model's ability to do something weird or unexpected that can track and precede the model's progress there, so we're caught less by surprise. I want to try to use our understanding of what the model's actually doing in order to try to build some mechanistic interpretability inspired progress measures. So let's try to jump into doing that. Let's go back and look at the actual algorithm the model's learned to do modular addition. It's learned to embed the inputs as these frequencies. It's learned to use the neuron activations to multiply them together to get the rotation of both of them applied. And then when it maps from those to logits, it gets the rotation that is A, then B, and then back by C. If it gets these logits, then it's just able to fully do the problem. A particular thing I want to start here is if we look at the claim that the logits are cos of W A plus B minus C, then this is a cube of numbers where for every value of A, B, and C, we can exactly predict what this should be. For each frequency, we can predict what this is. And so our understanding of the algorithm predicts that the logits should be a linear combination of a specific cube of numbers. By cube here, I basically mean rank 3 tensor, and some linear combination of those, and the leftover bit of the logits just shouldn't really matter. This is kind of a wild prediction because A, B, and C can each independently range between 0 and 112, and so there's 113 cubed. I actually know how big 113 cubed is. 113 cubed is 1.4 million. So we're making a claim that we can explain this tensor of logits with 1.4 million elements with a linear combination of 5 sets of numbers, and the leftover bits don't matter, which is kind of a wild and strong prediction. So our first progress measure is just going to be literally doing that. Call this Logit Periodicity because we're basically making the claim that the logits are periodic in an interesting way. The way we do this, we start with all of the logits. We need to index into just the final axis. This has shape 113 squared by 113. Let's reshape this so that it's got shape A by B by C. I'm going to use inops, which is this magic library for making tensors behave nicely, but you really don't need to actually pay attention to the details of what's going on here. We can now define a set of causes where for each frequency in our list of key frequencies, we can create the cube of predicted logits, which is just torch.cos of the frequency times 2 pi over p times a plus b minus c, where we can define a, b, and c as integers that vary. We want them all to vary independently, so we will use the magic properties of tensor broadcasting, where we have a B, and C axis. Fingers crossed, this should just totally work. And let's also normalize. So it's got norm1. A cute property of this tensor, which I'm not going to bother proving, is that the way this works is that we can think of the logits either as this A by B by C cube or as a 113 cubed dimensional vector. And if we do that, then each of these predicted logits are orthogonal vectors. And we can just figure out the coefficient of all of the logits with respect to each of those by just taking the dot product. So let's do that. So what I've just done here is I've gone through each of these key frequencies. I've got the set of logits that they predict is going to happen. And then I've taken the full set of logits, figured out what the coefficient of these predicted logits is. I can normalize it to get the cosine similarity, which is a metric for like how much of the logits is explained by this. And also calculated this approximated logits term for what's the like guess for the logits if we just only take these. What I found is that each of these 4 terms has like surprisingly high cosine similarity with the true logits. For context, if we just take a random vector, we get this pathetically tiny number because these are vectors in a 1.4 million dimensional space. But here we have like 0.27, 0.52, 0.19, 0.75, and the remainder is like non-trivial, but not that big. To verify that this is basically reasonable, that we can kind of ignore the residual, is so I have this function test logits, which takes in a logit-shaped vector and tries to figure out like what loss it would get. And if I feed in the approximated logits, we see that the loss goes from where it was originally, 1.6e minus 7 to 4e minus 8. So very dramatic improvement. We can now go and look at this during training. The thing I want to look at here is what fraction of the logits is explained by each of the predicted terms for each frequency over the course of training. Because if the model is just memorizing, it should basically have very little. If the model is actually learning the frequencies and like learning the generalizing solution, it should have a lot. Another way of phrasing all this is just, if you think you actually understand the model, then you should be making pretty damn strong claims about what every aspect of it should look like. And in this case, we're making a pretty damn strong claim about what the full set of output logits looks like. One important caveat to this claim is that we do know that the model performs well. So given the statement that the model performs well, any algorithm that works should give logits that have some correlation with any other algorithm that gives logits that work, just because they're both going to have high numbers on the correct answer and lower numbers on incorrect answers. But that does not explain the level of alignment we see. The claim I'm making is that if we want to ask the question of A, how much is the model learning the generalized solution? But also B, how much is it learning the generalized solution for a specific frequency? Looking at these two numbers of how big in absolute terms is that part of the logits and what fraction of the total logits is explained by that one is just a pretty strong metric.
One thing I would be interested in discussing or hearing about, what were like your best incorrect ideas while you were analyzing this?
That is a great question. Did I have any actually incorrect ideas? So I spent a lot of this investigation just being like a bit confused, having stuff that seemed kind of promising and just continually chasing all of that down, which is kind of a different vibe than actually being wrong about something. One concrete thing I was semi-wrong about is, so if you look at this last step of the algorithm, where we're producing logits by multiplying by cos WC and sin WC, this took me like several weeks longer to notice than the rest of this algorithm. The reason for this is that, in some sense, by the time you've gotten to the end of the MLPs and you have these directions in space, you've kind of already won, because you have numbers that are a function of the correct answer. Exactly how it goes from this to the output, I'm like, that can't be that hard a problem. So I spent ages thinking it just learned some kind of weird-ass linear regression, and noticed some weird anomalies, like the neuron logit weights seem to have a surprising amount of periodic terms in them, but never thought that hard about it. Some amount of the metrics I'm going to show rely heavily on this insight, like the one I'm currently making. Some of them don't. I think I made lots of assumptions that things would be cleaner than they were. I'll talk about those later as we start to see interesting results from the progress measures. I'm going to do a bit of a time skip where I go and code up nice vectorized versions of these things that I showed earlier. Cool. So what I've just done is written some somewhat more vectorized and efficient code to calculate this number and this number for every frequency for every checkpoint, which only takes a few seconds to run. I've made this function called getMetrics, which just runs this function on every model checkpoint and then stores it in this dictionary called metric cache. We can plot the coefficients for every frequency over the course of training. So there are two interesting observations when we look at this. The first is just to sanity check. The model we were studying was at the very final epoch, and let's just check that these coefficients do basically match what we had earlier. 21,070, 21,070. I have not fucked up the code, always a good start. The next interesting thing is, if we return briefly to the actual loss curves, we see the model has fully memorized by epoch 1,500. The model starts to like really grok at about epoch 10,000, and the model has fully grokked by about epoch 12,000. Let's take the graph below and add on lines for each of these for reference. I'm just going to go write a add lines function. So I just wrote some extremely hacky plotly code to put in some vertical lines at what I'm going to claim are the three phases. For reference, if we add these to the loss curve, we basically see memorization ends, starts to actually generalize, finishes grokking. Notes that between this, it goes from basically uniform to loss 3e minus 7, which is insanely good loss and wildly overkill. But before this line, it's just worse than random. Now, if you look here, it's like, okay, the model is A, clearly making interesting systematic progress towards the correct solution before it gets better than uniform loss. even before it finishes memorizing, it seems to be like potentially going somewhere. And the second interesting observation is that it's not the case that each of these lines just kind of goes up in a perfectly correlated way. There's some weird ass circuit competition and form, like where initially 25 is like totally dominating and 47 hasn't budged that much, and then they switch places. And during grokking, 25 becomes like less significant. And these two, which are 27 and 50, are like reasonably significant here, and then just basically go down to near zero. And it's like, what? I should add the caveat that I haven't been particularly epistemically virtuous here because I haven't normalized by how big the logits are. So some of these results could just be logits get big and actually everything gets big. So let's look at the cosine similarity, which is more like what fraction of the logits are explained. And we see that it like mostly looks the same. It is also just interesting that even while the model is clearly memorizing, and during the period where the test loss is like actively going up, the model is still beginning to learn like part of the correct solution. A final interesting thing to check is adding in the residual cosine similarity. So what's the fraction of the logic explained by the term that isn't explained? I'm just going to go write some quick code to do that. I redid the above analysis and now included the residual term. We see that initially stuff that is not explained by the predicted logits is like basically everything, which is what you obviously expect when you have a tensor in 1.4 million dimensional space, but well before the point where the model gets better than random loss, it's like crashing and continues to go down during the period where we see test loss crash, but like, it goes down less here than it went down throughout all of this. So that's progress measure 1, Logit periodicity. It's worth zooming out a bit and trying to think about what are our hypotheses for what's going on? Why does grokking happen? And what is actually happening during grokking? So the claim that I try to defend in the paper is that we can break things down into 3 phases separated by these vertical lines-ish: memorization, circuit formation, and cleanup. During memorization, the model just fits to the training data and does terribly on the test data. It's like not immediately obvious why memorizing the train data means it should do worse than uniform on the test data, but intuitively the reason this happens is that random loss on the test data means you're outputting every possible answer with equal probability. But if you're confidently memorizing everything else, you've got no reason to keep things at even probability for every possible answer. So when you have no incentive to make the test loss uniform, it's going to get way worse. Then we have this period where it seems like things basically plateau. But if we look down here, we see that the model is clearly forming the correct circuits during this period. And it's making steady progress, even though here it looks pretty flat. This is the phase I call circuit formation, where the model is continually forming the actual trig-based generalizing solution. One important thing to note is that when you look at this, it like kind of looks flat, but if you zoom in a bunch, it is like fairly steadily going down, even if it's not going down that much. And if we look at the test loss, it's also like reasonably steadily going down, even though it's like wildly worse than random. So my story for what's going on here is, so we're training these models with pretty heavy weight decay. And weight decay creates an incentive for the model to be simpler, to have smaller weights. So the fact that it eventually ends up with a generalizing solution clearly suggests that the generalizing solution is simpler than the memorizing solution. I don't currently have a proof of this, but if you look at the algorithm, the generalizing solution is pretty sparse and only uses a couple of directions in space. so it seems pretty non-crazy to me that it's pretty simple. But something weird happens, where even though the model ultimately prefers the generalizing solution, it first gets the memorizing solution. And I don't feel like I fully understand this, but my best guess is there's just some property of the space of possible models that makes getting to the generalizing solution harder and slower than getting to the memorizing solution. My intuition is something like, in a careful algorithm like this, you need to have lots of bits of the network lining up, and where, say, the model's only incentivized to learn this representation when it's got the neuron weights that will lead to them being multiplied, and when it's got the neuron to logit weights that lead to them producing the correct logits. There's like not a strong incentive to get any one of these correct in isolation. And so we might expect that the model will very slowly learn each of these with like a very weak gradient signal because the other bits are like there a little bit. As each of them gets stronger, then the gradient signal to learn each of the others gets stronger. And so initially you're getting there really slowly, but then the further you get, the like stronger the incentive is to learn the generalizing solution, and things slowly speed up over time. And so under this framing, the model ultimately prefers to get to the generalizing solution, but it takes a longer time to get there. So it gets the memorizing solution first, but then there's this long phase of circuit formation where it's slowly transitioning from the memorizing solution to the generalizing solution. My guess is that what's going on is it's diverting some parameters to the generalizing solution such that the logits are kind of a combination of the generalizing and memorizing solution, and where it's slowly dampening the memorizing one. The reason that the train loss goes down is actually kind of subtle. So the model has two incentives. The model is being regularized, it's got an incentive to be simpler. The generalizing solution is simpler, but plausibly there are some aspects of the problem that make the generalizing solution harder to reach. And the model only marginally prefers the generalizing solution, so the incentive to be simpler is kind of weak. There's a great bit of work from Adam German and Buck Schlegeris forming a toy model that predicts that many problems, which involve like circuits with different bits cooperating in different layers, are going to form as a phase transition, or what they call an S-shaped curve, where it's initially really slow, then develops fast, then plateaus, which I'll link in the description. A final interesting connection there is there's this wild result called the lottery ticket hypothesis, which says that if you take a trained network, you can often kind of predict which parts of the weights are going to actually matter, even at initialization. And that if you just delete everything apart from those weights, so like have a much, much smaller model, then it can still generalize just as well. And I believe in some cases train faster. And that in this worldview, the reason bigger models can do better is just they've got more room to have winning lottery tickets. And just that the space of like possible weights is extremely high. This seems like something like this could be an important part of what's going on here, where each of these components, like getting the representation right, getting the multiplication right, getting the map to the logits right, there's like some direction in weight space that does that. And then lots of directions in weight space that kind of do random crap that kind of cancel out but add a lot of noise. And the model slowly learns to select and focus on this winning, generalizing lottery ticket over time. And then there's some really weird shit where there's actually 56 different possible lottery tickets, and the model decides to use some but not others, and then kind of switches between them, and who knows what's up with that. Returning to the story of what's going on in grokking, the model is slowly ramping up the generalizing solution and ramping down the memorizing solution. It's kind of wild that the model can even do this, since they are not designed to be modular in this way and able to like slowly shift their output as a linear combination of two things. So the reason that the loss curve has a kink here, where it goes from getting better very rapidly to leveling out, is you can kind of think of there as being two pressures on the model. One pressure is to perform well on the training data. The other pressure is to have simpler weights. So here, the incentive to get better on training loss is really, really high compared to the incentive to get smaller weights. But here, they eventually balance. And it's important to note that they have to balance, because here the model's got perfect accuracy. So if you just keep multiplying the logits by 10 and keeping everything else the same, it's going to get better and better at the task, because it's just going to make the correct logit even further away from all of the incorrect logits. And so the fact that it's level off suggests that these two forces are basically balanced. But the model can slowly improve at training loss, because on a simpler solution, they're going to equilibrate at a smaller point. Here, 1e minus 7 rather than 3 minus 7. So what's going on is that as it slowly increases its reliance on the simpler solution, it can kind of just increase the total amount of logits and stuff the model has, while preserving the same kind of net balance between the two. So the final question is, why does test loss take this long to get better than random, given that the model has basically learned the correct solution well before then? This is the phase I call cleanup. So what's going on here, I believe, is that the model has these memorized logits. It's got this memorized circuit, but still has a significant impact on the logits. And as noted here, the memorized circuit is way worse than random. So it just adds a ton of noise that completely kills the ability to predict the test data. So even though there's a component that's like actually pretty damn good, the fact that there's all of this memorization noise and crap means that it's still pretty bad at the test task. But eventually, it gets so good at generalizing that the memorizing parameters, the like memorizing circuit, it's starting to add more complexity in terms of increased weight norm relative to the improvement in train loss that it gives the model. So the model decides to significantly increase the generalizing circuit and significantly suppress the memorizing circuit. And now the generalizing circuit is like strong enough that it starts to really matter for the test data, and this crashes. Then things basically plateau when the model's in a new equilibrium. The model clearly hasn't fully cleaned up the memorizing circuit, because train loss is still better than test loss, but it's like now pretty damn close. A bunch of the things I've been saying here are kind of conjecture or based on things I haven't fully supported, like what does it even mean for the model to be redirecting parameters from the generalizing circuit to the memorizing circuit? My personal guess is that there are kind of directions in weight space that support the memorizing solution versus the generalizing solution, and it's kind of scaling up one and scaling down the other, rather than like literally repurposing some neurons for one versus the other. But also, what do I know? I think there's loads of interesting open questions here of like refining what's actually going on. But this is my best guess, and I want to spend the rest of this tutorial making 2 more progress measures that can help us narrow down what's actually going on.
The original Grokking paper from OpenAI in whenever 2021, which feels like so far ago in AI years.
Yeah, if we were doing pure maths, it would be like, 30 years ago.
Yeah. Well, maybe even longer. But did the original Grokking paper do any analysis on interpolation between generalization and memorizing?
I don't believe they did. Yeah, my interpretation of the original Grokking paper is that it's very much, here is a fascinating and unexpected empirical phenomena we discovered. Let's do a bunch of analysis of like how it happens, what kind of things affect it, and just try to like really make sure this is a real legitimate thing we found. And they had like a little bit at the end where they were doing a bit of analysis of the representations the model had learned. But
Yeah.
to me, the like focus of the paper, which I think is like a correct focus, is just, here is a weird ass phenomena. Let's make sure it's actually happening and communicate this.
Yeah. Do you know any other work that talks about interpolation between generalization and memorizing?
Nothing's coming to mind that I think is explicitly studying this. There are several other grokking papers trying to understand grokking that all give different kinds of analysis on this. 2 ones I particularly liked were from, I think, Ziming Liu in Max Tegmark's lab, there was this paper called something like Towards Representation Learning that was trying to look at how the model learned the correct representations in the embedding, and had the interesting claim that grokking was just kind of an intermediate phase as you varied hyperparameters between totally memorizing and totally generalizing. And this paper called Omnigrok from the same group that found that if you took kind of more conventional ML tasks, like some forms of image classification and some forms of language modeling, and you make the weights of the model just incredibly big at initialization, then sometimes this will grok, and I'm like, what? And I think both of those would have thought a bit about these questions, but I'm not aware of any like deep dive study that I feel like I've been excited about and got insights from. Got insight from is harsh. Papers that I've read where I'm like, cool, I feel like I've actually understood this and significantly refined my understanding of it.
Word. Okay.
One thing I'm hoping is that just with this tutorial and the code with the paper, is that people who are reading this, who are interested in it, can just go and try to figure out these questions. Why does this happen? Why does it memorize first and then form the correct circuit way slower and then eventually switch? What?
Yeah.
Feels like the kind of thing
Yeah.
someone should be able to answer, at least in this specific case of modular addition.
Yeah, and then at Neil on Twitter, and I'll read it.
If you do some exciting work here, I will totally retweet you. I'm aware of like some people who are poking around at this, though I'm not sure if any of them are specifically working on the question of how can it go from memorization to generalization.
Yeah, it's a weird question.
Yeah.
It's not really clear even what it means.
So this is my narrative of what the hell is up with grokking. The next thing I want to poke around at, two things I want to try to answer. The first is, how much is it the case that the model, say this point in training, would be great at generalizing if we could just clean up the memorization for it? And the second question is, how much of the model's ability to perform well on the training data is coming from the generalizing solution rather than the memorizing solution? I want to use my understanding of the algorithm to come up with two metrics that get this. So the first one, how good is the model at the task if you artificially clean up the memorizing solution for it? I'm going to call restricted loss. I don't know why I'm phrasing all this like I'm coming up with them on the spot. It's totally things in the paper. So the idea of restricted loss is if we look at the neuron activations of the model, I'm making the aggressive claim that the things that matter in the neurons are these terms, sine w a plus b, cos w a plus b, for these four values of w that I care about here. There are 113 squared pairs of a and b, so I'm basically claiming there are like 8 directions that matter and 12,000 minus 8 directions that don't matter. It's worth emphasizing this point because I'm actually doing a kind of weird thing here. So if you look at the neuron activations and their shape, the shape of the neuron activations is 113 squared, which is the space of pairs of A's and B's, by 512, which is the number of neurons. I'm specifically saying that in this 12,769 dimensional space, there are 8 directions that matter. This is actually a very weird claim to make, because this is a batch dimension. And thinking about directions in batch space is kind of weird. Normally, you just think of each element in a batch as a kind of unrelated thing from every other input that is just kind of like points chosen, the data distribution. But modular addition is a really weird problem, where it turns out that rather than thinking of the inputs as just like kind of separate numbers that can kind of be understood independently, actually the thing we care about is these directions in input space of sine WA and cos WB, etc. The claim I'm making is that I should basically be able to restrict the neuron activations to just the directions I claim matter, map these to the logits, and get good loss. So let's just go and do this. All right, so the slightly convoluted code that I've just written is because we can think of the neuron activations as for each pair of A and B, there's this set of numbers, there's like 512 neuron activations, and I'm claiming that you can usefully think about this as having directions in the space of like all possible inputs. So as we were doing with individual neurons, we can do a 2D Fourier transform on this, where the exact details are not super important, but the relevant thing is that if we look at this diagram, the interpretation is each Fourier component across the A and B input space. So that's a function like cos 17a times cos 17b. X means B and Y means A, sorry. Each of those corresponds to a vector of neuron activations. And you can kind of think of the like inputs A and B as being kind of rotated to give us a set of neuron activations for each of these periodic functions. This is just like a mathematical claim that for any function on pairs of integers between 0 and 112, you can do this. The interesting observation is that, so what I did here is I then took the norms of the neuron activations for each of these components. We basically see that the terms for like a key frequency, where you take the product of a trig thing in A and trig thing in B, are big. The terms of this frequency, which are constant in A and have a trig term in B, are significant, and basically everything else doesn't matter. There's also a constant term, but I got rid of that because it's not that interesting. Just like a bias term across all inputs. So I showed diagrams like this earlier, and the key observation I want to make is that assuming that this is actually what's going on, and assuming that these things don't matter, we should be able to just restrict our attention to the terms along the diagonal. We can actually go one stronger and restrict our attention to the components that are sine W A plus B and cos W A plus B, which are the sum or difference between terms in this block along the diagonal. Let's just do this. Cool. So the somewhat convoluted thing I just did is I took the neuron activations, I then looked at the component corresponding to sine W A plus B, cos W A plus B for each of the key frequencies, took the component of the neuron activations that corresponded to those, and deleted everything else. And here is some grungy tensor manipulation code that does that. We really need to care about the details. I also kept the average of the neurons term, which is basically just used as a bias. And I just directly mapped these to the logits, and when we evaluate the loss on these restricted logits, we see that the loss has gone to 2.2 e minus 7, and if we compare this to the original logits, the test loss, it's like basically the same, has gotten slightly worse for reasons I'm guessing aren't actually that interesting. But this is totally on my list of stuff where I'm pro someone going and poking around at this and seeing if I'm missing anything important. My guess is there's something like the model is subtly using some other frequencies a little bit, or there's, yeah, I basically don't have a great story beyond the model is subtly using some other frequencies.
Quick plug for the 200 concrete open problems in MI.
So one of my irritatingly effortful side projects at the moment is I'm running the sequence called 200 concrete open problems in mechanistic interpretability, because I think there's just so much low-hanging fruit here that someone who's interested in reverse engineering systems and has some time to learn and skill up, but doesn't necessarily have a great ML background, could go and do something interesting and find something cool. I wanted to put my money where my mouth is, so I challenged myself to write a sequence with at least 200 of problems that I thought someone might be able to go and hack around with and get something interesting. And in the description, I'll link to the sequence and also link to the bit in the sequence on training dynamics. I try to categorize the sequence into different areas of open problems, and then put far too much effort into trying to flesh out the area and how to think about it, and like why I thought the area mattered. If you're interested in mechanistic interpretability, you should go poke around that. I'll also link to a guide I wrote on getting started in mechanistic interpretability and what kind of things you should learn, skills you should care about, etc. So now let's look at this during training. I'm going to do another brief time skip. So turns out I had a bug in my code. Earlier in my code, I didn't have this .clone, and this meant that when I reshaped the neuron activations, this is the same tensor. And PyTorch did not bother copying the memory, so that when I did this, I edited this as well, and I hate tensors. Things are now good, and we can go back and actually figure out the restricted loss. We get something that's actually even better than the regular loss. Okay, so I just plotted restricted loss over training, and it looks kind of weird. Turns out, in particular, like what, and also doesn't really proceed that much. If we compare this to the restricted loss graph we had in the paper, it's like, okay, that's clearly massively preceding test loss. But it turns out that I forgot one of the steps, which turns out to actually be pretty important. Logits can sometimes have an important average term, like an important bias term average across all inputs, and sometimes this can matter. In my opinion, this is like not an interesting part of the overall algorithm. It's just the model being like, I should systematically boost logit 5 over logit 7 for all inputs, for some reason. And it turns out that if I uncomment this line and add this in, and then rerun everything, then suddenly we get a graph that's like way closer to this. Why does this matter? I have no idea.
Can I ask a quick question, which is like
Yeah,
the
go for
boosting
it.
effect of logit 5 over logit 7, how does that change throughout training? Like, is that boosting more present at the beginning and it gets trained away? I would imagine yes, maybe no.
This is a great question. So it is presumably the case that some output tokens occur more often in the training data, just like random chance. And so the model wants to learn a bias that favors those when it's memorizing, but doesn't care when it's
Sure.
generalizing.
Sure.
Another idea is just that like memorization is kind of weird and janky, and it's probably going to, like, the way I think of memorization is kind of like the model fitting a weird convoluted curve through a bunch of points, but much messier in a way higher dimensional space. And this will probably lead to just things being kind of messy and uneven and not very symmetric, especially since the training data is just like a bunch of randomly chosen things to add up. The confusion I'm trying to explain here is, why would it ever be the case that the logits have a bias term favoring some output
Yeah.
tokens over others? Because like everything
Yeah.
to be symmetric. But like
Yeah.
if you haven't learned how to generalize, they shouldn't be symmetric. I am like kind of surprised by how much this matters. In my opinion, extracting a bias term from the logits is not an important part of the model's computation because it doesn't depend on the inputs. So this feels like probably not cheating.
What do you mean by cheating?
That is a good question. What do I mean by cheating? So when you're trying to reverse engineer a system, it's really easy to allow information to leak in. Let's say I wanted to make the claim that actually the Fourier cos A plus B components of the neuron activations are all that matters, and I do this restricted loss thing, but I still add on the residual stream that comes via the attention. It's plausible that what's actually going on is the models just learn to do the entire algorithm using just the first attention layer, and is just inserting this in some weird-ass way, and that the neurons don't actually matter, and that if I deleted all of the neurons, things would also be totally fine. To me, that would be an example of cheating. Making a claim that what I'm doing is conclusively telling me what the model's doing, but there are ways it could be smuggling through computation that I haven't explained. But I think that allowing it to smuggle in a function which depends on the inputs is much more concerning than allowing it to like create a bias term.
And I guess the thing that this makes me think of is like, so you would certainly have a better wording for this, or maybe you explicitly disagree with this. But my kind of view is that it's very damn hard to, it's so hard as to be basically impossible to conclusively 100% prove something in mechanistic interpretability, but you can kind of get like more and more evidence about something being true or evidence about something being false. And there's a notion I have of like, I guess like the minimum effective dose, to borrow a phrase, where it's like, how much evidence do I need to understand the circuit or circuits such that I can understand what's going on for my purpose? How do you think about it? Does that kind of resonate?
So I do agree that proving is an extremely high bar and probably an unreasonably high bar. And
Yeah.
there was always going to be some amount of like weird, messy shit and an infinite series of rabbit holes you can dive down. I do think there are some things that you can show with like a pretty high amount of confidence. Here, the fact that with just a bias term and 8 directions in input space, I've like got good performance, I think is like pretty strong evidence that the other stuff just doesn't matter. Yeah, so I think you can get pretty good evidence. I think that also a really important skill is being able to look at the evidence you have and try to break it. For example, one of the things I'm doing in this kind of messy restricted loss code is I'm making it so the neuron activations are only a function of a plus b mod p, because sine a plus b and cos a plus b are only a function of those. So the output of this should now be like symmetric. It should now like only be a function of the correct answer. And having it be highest on the correct answer is harder. This is still telling me something real. And the fact that doing this actually improves the performance is also telling me something real. But
Yeah.
there are like worlds where this is telling me something misleading. And I think it also depends on like how high your standards are for the question you're trying to answer. I think it's much easier to answer questions like, is this like a thing that on its own would be sufficient to solve this problem, or an important part of how the model is solving this problem, versus is this the entirety of how the model solves the problem?
Yeah.
The second is way harder to answer because there could totally be 2 bits, each of which on their own is sufficient to do the problem, and another bit which is like suppressing the answer. And if you ablate the suppressing term and either of the 2 bits doing it, then it looks like the bit that's left was sufficient on its own. And I don't know, generally just thinking about causal interventions in complex systems is kind of hard. Redwood Research has this great new piece of work called causal scrubbing that's one of the better attempts I've seen at doing this, but it's still definitely not perfect and wouldn't help in this particular use case.
I think there's just also like so many fucking neurons in like realistic neural nets that it's just like unrealistic to be like, I understand everyone. And there's probably like subtle fuckery that adds a little bit of performance or something, even when, you know, you understand the gist of what's going on.
Yeah, one of the things that's kind of annoying about MechInterp is it's such a young field that there isn't clear consensus about what it even means to understand a circuit, or what the right standards of evidence are, or even like what is exactly the correct question to be answering. So I've invented a bunch of my own somewhat ad hoc techniques in this investigation, some of which are pretty specific to the weirdness of modular addition and all of the Fourier stuff that's going on. In the curve circuits work, the OpenAI interpretability team wrote Python code to generate the weights for the curve detecting neurons they claim to understand. In Redwood's work, they've been doing lots of these causal interventions where they patch specific activations from different distributions into each other and use this to isolate out which aspects of the input actually matter for which activations in the model. And I think this is another compelling form of evidence. And yeah, this is annoying. I would really like there to be some gold standard technique that everyone agrees is the best way of doing things, especially if we want lots more people to come and be involved in the field. Causal scrubbing is the best attempt I've seen at this, though different things you think you understand about a model behavior can just necessarily involve weird ad hoc approaches, or like pretty different approaches from other things you might try to explain. I'm pretty wary of trying to jump to claims about universal techniques or universal metrics or interpretability benchmarks, just because I think it's so easy to lose sight of what's actually true about the model's internals and come up with some metric and then good heart yourself and just achieve the metric.
Yeah, I mean, there's a lot more to say there, but in the interest of time, I'll stop my line of questioning.
Sounds good. Yeah, it's been on my mind since I'm currently writing the building techniques and automation post in my concrete open problem sequence and trying to disentangle in my head what do I even think of the right forms of progress that should be happening in making useful techniques. Has been an interesting experience. All right, so let's resume staring at this diagram. This is restricted loss. Intuitively, the way restricted loss works is I've artificially cleaned up the like memorization bit of the model circuitry for it and let it just use the directions that matter for the generalization circuit. This is a slightly messy claim because what I've actually done is taken 8 directions in 12,000 dimensional space and deleted every bit of the neuron activations that weren't in those. Some of those could have been being used for memorization in some weird way, but 8 is such a small fraction of 12,000 that, I'm kind of happy with this approximation. And what we see is that, first off, the entire rise of the test loss during the memorization phase just isn't really there. And actually, it is improving to better than uniform. This is probably a consequence of the fact that if we go back to the cosine similarities, we see that even during memorization, it is learning all of them, but especially frequency 25. Though, again, all valid solutions to the problem will slightly correlate, so the baseline similarity you should expect is like above 0, but 0.1 is high. So we see that if we clean up the memorization stuff, which is making things be very non-uniform, it's actually like kind of okay. And then throughout this entire period, it's going from okay to like actually pretty damn good at the problem, even when the test loss is like way worse than uniform. And this is a pretty clear marker in my eyes that it is forming the correct circuit. And then eventually it's just like starts to go down dramatically. So like this, the fact that it starts going down is interesting and suggests that the circuit formation cleanup story is not fully clean, is not like fully a precise description of what's going on, because the fact that this is dropping is definitely evidence that there's some amount of further circuit formation happening. But useful thing to note is that the cross entropy loss that you get when you know the correct answer, like you've got greater than 50% probability on the correct answer, is like 0.7, which was achieved here on average. We really should be looking at the accuracy for this, but whatever. Once the model gets perfect accuracy, the way you improve loss is you just scale all the logits up. So very plausibly what's happening here is that the model is just, once it's decided to stop using the memorization part, it can just significantly scale the generalizing logits. There's probably also some amount of it's just continuing to form the generalizing circuit and making it cleaner. But importantly, the fact that these two diverge and then kind of converge suggests that here, the main thing harming test loss is the fact that it hasn't cleaned up the memorization stuff, and then here things become better. One way we can operationalize this better is by actually plotting the ratio between test loss and restricted loss. Yeah, and what we see when we do that is like ratio slowly climbing, peaks around the time cleanup happens, and then crashes. There's also this weird thing where I'm not super sure what's going on there, but I'm guessing it's something like there are some frequencies that matter that haven't been captured by the key frequencies, and that by restricting to only the 4 key frequencies we're studying, we're missing out on stuff. I can just cross-reference this here, And yeah, it looks kind of like frequency 27 and 50 matter, but they basically stop mattering by here. So this hypothesis could easily be wrong. Networks, that's full of so much weird mystery. I'm going to say I overall feel reasonably happy with the claim that this helps to show that if the model was purely using the generalizing solution, it would be pretty damn good well before the Grokking point. And the thing that's harming it is the fact that it has lots of gunk that isn't generalizing. How happy do you feel with that, Jess? All right.
Unmuting feels great.
Great. All right. So the final progress measure I'm look at is what I call excluded loss. If we remind ourselves of what the loss curves look like, I made the claim that during this range, the model is slowly transitioning from the memorizing solution to the generalizing solution. Restricted loss is evidence that the task performance is improving from the generalizing thing, but it's being harmed by the memorizing thing. But it says nothing about what's happening to the training performance. And it's kind of a surprising and non-trivial claim that the model can preserve basically constant train loss while transitioning between two completely different ways to compute good train loss. So the metric of excluded loss is basically the inverse of restricted loss. We're going to remove the directions in neuron activation space that correspond to the key frequencies, and we're going to see how train performance changes. What this model predicts we would see, though I probably shouldn't use the word predict because I developed this model after finding these progress metrics and staring at them, is that the model's excluded train performance should be pretty close to train and then over the course of this significantly diverge. So let's go and calculate this. I feel like I should be able to basically just copy this. And this time, when I have my approximated neuron activations, I'm going to get rid of the part where I add on the mean of the neuron activations. And now I'm going to take the excluded neuron acts as the neuron acts minus the thing we got via the restriction process. This time I'm going to look at the train performance, and it's catastrophically bad. I will again note that what I've done here is removing 8 directions in 12,000 dimensional space of like all of the inputs, and it sent the loss from insanely good 1e minus 7 to like 7.5, which is appallingly bad. So let's calculate this over training. So briefly going back in time, it turns out that I had a dumb bug in my restricted loss calculation code because the original code said W logit here, which is calculated from the final model rather than from the relevant model checkpoint. So I updated it to do that thing correctly, and we now have this like fairly similar looking curve, but like somewhat different looking, and gets rid of some of the weird anomalies. Why is it the case that W logit for the final model just kind of worked? This is not super clear to me, but I would basically guess that the generalizing solution just doesn't actually change the directions that matter that much, or something, and that the hard part is learning to get the directions sin A plus B in the neuron activations, and the neurons this corresponds to doesn't change that much. But I would not have expected this. This is interesting and surprising. And I guess the caveats to all the stuff I was saying earlier is just restricted loss goes down significantly faster and more sharply. It has this weird bounce down here, probably because of some specific flavor of Adam W, where making train loss go down has momentum, but accumulates gradients via exponentially weighted moving averages. The weight decay doesn't, and so it probably overshoots its mark, and then weight decay like pulls it back a bit. And there's no longer the weird kind of diagonal thing where it's like worse than test loss for a bit. Then there's this weird thing where it slightly rises over time relative to train loss. Why does this happen? I have no idea. This is what I get for trying to code things from memory. We can also look at the ratio graph and hopefully get something more compelling. Okay, cool. That's like way more what I expected this to look like. Restricted loss is kind of like a bit better than train loss, and then dramatically spikes near cleanup when the generalization circuit is pretty good and mature, and then crashes once it's like actually cleaned that up. Note that this is a log scale y-axis. If I unlog it, you get this beautiful graph. So that was embarrassing. So let's get back to computing the excluded loss, where I noticed this because everything broke. Cool. Okay, so something is broken. You don't really get how it's broken. All right. So turns out that I have the somewhat embarrassing bug of forgetting to set a random seed before I took my training and test data, which means that since I've restarted this notebook since the original training run now, this means that the training and test data I currently have, this is not the stuff the model is trained on, which means that metrics that try to look at the training set are just completely broken. And this is not great. Fixing this is something that seems like it'll take too long to do right now, but I will fix before I publish the notebook accompanying this. So in order to close things off in a tragically less satisfying way, let's go look at the excluded loss graph that we have in our paper. And what we basically see is that the excluded loss goes down alongside the train loss, starts to diverge a bit towards the end of the memorization phase, since the model's kind of starting to form circuits in the background a bit. But then over the course of the circuit formation phase, it like dramatically diverges, even as the train loss remains the same and goes down slightly. And then by the time cleanup happens, it doesn't really change that much because generalization has just become so important. And yeah, I think we should probably wrap things up there. Just a few closing words. The spirit of this tutorial was actually implementing the stuff we did in this paper is not that conceptually hard and doesn't take that long. Well, okay, those are kind of relative statements. It is doable, and you can watch it and follow along and see what happens, and you could go and try doing an investigation like this yourself. It was the intended spirit of this video. And if you want to go see the polished, careful things that actually display our results as strongly as we're able to make them, you should go read the paper and look at the accompanying code, because that was not under the harsh constraints of can I approximately live code this? I hope people generally enjoyed and found this useful. We will link to a bunch of the various resources mentioned in the description, including the paper, this notebook I made and the accompanying collab, and if mechanistic interpretability is something you found interesting and want to go learn more about, or maybe try doing research in, I will link in the description to a post I wrote on how to get started, and the post we discussed earlier on 200 concrete open problems, something like you could go work on. And yeah, thanks a lot for watching. Why does it think that the answer is different from the answer up here?
Torch is trying to be optimal and is using 2-bit floats. So it's just a floating precision error.